Hi, this is a video about how to design batch control systems according to ISA-88. I'm James and I've been working on batch control projects since before this standard was even published. If you want to know what batch control is all about, then you've come to the right place. I'll explain everything you need to know about the ISA-88 standard and all the stuff to avoid. A basic knowledge of process engineering is going to help you, specifically an understanding of process flow diagrams and P&IDs. Let's start with some basics. Batch manufacturing is a type of manufacturing that is characteristically procedural. In industry, the processing is typically carried out in one or more vessels, ending up with a fixed amount of product after each procedure. Here's a simulation of a typical small-scale batch manufacturing process with some common activities, like quantifying and adding ingredients, multi-step processing in a general-purpose reactor, transferring between vessels for different types of processing. And finally, storing a fixed lot of the product with a unique reference for traceability. This would be a typical batch process. And what is the ISA-88 standard? Well, shown here is the formal name of the specification with some shorthand alternatives. I'll stick with the old school terminology, S88, which is a legacy of the pre-release version. Notice this is part one of a set of standards, but that is the part everyone means when referring to S88. There have been two versions, the original one dated in 1995. That one was adopted as an international standard. The second version dated 2010 was not, so I'll only relate information that is consistent across the two versions. Please note, S88 is not a software standard. S88 is more about how to present information. The information in this case being the control requirements for a manufacturing plant. Process designers must make the control requirements intelligible to the users of that information. That could be production experts creating operating procedures or automation engineers designing software. Obviously, stating the requirements in an unstructured and inconsistent way is going to make the user's job much harder. But even well-structured but proprietary ways of representing the information can introduce a learning curve to each new project. So S88 is an attempt to standardize the presentation of control requirements across the batch manufacturing industry. To do this, it has two main aims. Firstly, to standardize the language we use to define the requirements. This is the terminology part of S88. And secondly, to categorize and structure the data in a standard way. This is the purpose of the models. Here's a roadmap of the topics to be covered to understand S88. The control requirements for a batch plant are fully specified on completion of the equipment entity design. For a specific product, completion of the procedural control design will fully define the production cycle. To arrive there, we start with the generalized structures called models in S88 and customize them for each particular plant and product. Along the way, we need to understand three types of control requirements: basic control, coordination control, and procedural control. Finally, we need to understand that there is a link between the procedural control and the equipment. The physical breakdown of a batch manufacturing plant is fundamental to all other design activities. Based on the physical model, S88 tells us how to break down and categorize the physical equipment resources of a process plant in a consistent way. Before describing how to define the physical design, we should first consider why is it desirable to break down a processing plant according to S88. Okay, let's consider the example batch process from the introduction. This is a sequence of processing actions across 3 pieces of processing equipment guided by a procedure. On the face of it, this seems to work pretty well. However, notice what the reactor R1 is doing during drying and discharging. Both the vessels on the left sit idle, waiting for the procedure to complete. Clearly, this is not optimum use of the equipment. So, consider the situation when the dryer has just been loaded from the reactor. If we isolate the dryer as a separate unit of equipment along with the dryer-specific part of the procedure, then those actions can now proceed independently. We can turn our attention to the reactor, which can also be controlled as a separate unit. This allows us to start on the next batch. Now we can see that the plant is better utilised. But there's one more improvement that's possible. Notice that after the addition of the first ingredient, the reactor has to wait on the second ingredient being added to the weigh vessel V1 before it can be charged to the reactor. We can improve on this by separating out the weigh vessel V1 and its minor processing task. This will allow further optimization. Vessel V1 can now be independently loaded while the first ingredient is being added to the reactor, eliminating the wait to add the second ingredient. In fact, there's nothing now to stop the weigh vessel being charged ready for the next batch. What we have just described in a nutshell is one of the essential ideas implicit in the ISA-88 standard: optimization. Having seen the reasons for breaking down the process plant, we can now return to describe the structure and terminology of the physical model aimed at achieving this optimization in a consistent way. Here are the 4 levels of the physical model and the criteria that define each level. A process cell contains all the equipment needed to make batches of one or more products. Units carry out major processing activities. Equipment modules carry out minor processing activities and are typically centered around a piece of process equipment. Control modules are the instrument and control devices contained in the other 3 levels. The quotes are lifted directly from ISA-88. Notice that all 3 upper levels are defined by the processing they carry out. In ISA-88, the physical model is described as being hierarchical, but that could be misleading. Think more of containers getting smaller from top to bottom. It doesn't imply that all levels must be present and fit inside one another like a Russian doll. For example, control modules may be contained in the process cell directly, in a unit directly, or in an equipment module. Likewise, an equipment module may be contained in a unit, as shown, or in the process cell directly. A process cell must contain at least one unit, and there must be at least some control modules. Interestingly, the equipment module is the only level that may be omitted completely. We've already analysed our simple batch process in an ad hoc way in order to demonstrate optimization, but we can now analyse it by following ISA-88. To illustrate a complete physical design following the guidance of ISA-88, we can start from only a process flow diagram of the plant and the following basic description. Some materials are to be added to reactor R1. One of the materials is weighed in vessel V1 before being added to the reactor. Some processing is carried out in the reactor, and the resultant slurry is sent to the dryer D1, where it is dried and the finished product is emptied into containers. Now, ISA-88 tells us how to break down this plant. We know from the physical model criteria that the highest level is a process cell, and it must contain all the equipment needed to make batches of one or more products. We can thus define a process cell PC1 containing the weigh vessel, the reactor, and the dryer, since together they can make batches of product. The next level is the unit. A unit is defined as a collection of equipment that can carry out one or more major process-orientated tasks. The reactor in our diagram fits that description, and since the dryer will dry the complete batch, we can assign that as a unit too. The next level in the physical model is the equipment module. Now, unlike the process cell and the unit, which are relatively easy to understand, the term equipment module is a bit abstract. I hope you'll forgive me injecting a personal opinion here. How much confusion would have been avoided if this had been named something like minor unit rather than equipment module. Equipment module sounds like a software definition, which has fed the idea that ISA-88 is a software standard. So we need to pay close attention to the criteria that ISA-88 uses to define an equipment module. It's defined as a functional group of equipment that can carry out a finite number of specific minor processing activities. Examples of minor processing activities given in ISA-88 are dosing and weighing. Also, according to ISA-88, an equipment module is typically centered around a piece of process equipment. The crucial points here are that an equipment module is defined by the processing it does and where it does it. Since vessel V1 is to be used to weigh ingredients, it qualifies as an equipment module on the grounds that it executes a minor processing task, weighing of material, and we can see that the process equipment where the weighing happens is in the weigh tank V1. Notice that I included the weigh tank equipment module as part of the unit. That is perfectly okay since it does seem dedicated to the reactor, but it's equally possible to make it part of the process cell but not part of the reactor unit. If we design it like that, then the weighing functionality could be shared with other units. We can choose that option and take it out of the unit. This again shows that ISA-88 has some flexibility built into it. Only the lowest level, control modules, remains to be identified. For that, we need to zoom in from the process flow diagram into a P&ID type representation of the reactor R1 with a bit more detail for the reactor. Control modules are the lowest level in the physical model, the term control module being a collective name for all the instrument and controlled equipment normally shown on P&IDs. These are actuated valves tagged as XV1 to XV12, regulating control valves, instrument transmitters for pressure, level and temperature, a high level switch on the vessel, a transfer pump and an agitator. Together they make up the control modules of R1. So here's what we've got so far in the physical design. A process cell PC1. PC1 contains two units, reactor R1 and dryer D1, and one equipment module, weigh vessel V1. We also identified all the control modules contained in reactor R1. Vessel V1 and dryer D1 will contain a similar assortment of control modules to be defined. I hope you see that creating a physical design is very straightforward if you stick with the definitions of ISA-88. Okay, to recap, a process cell contains all the equipment needed to make batches of one or more products. Units carry out major processing activities. Equipment modules carry out minor processing activities. and control modules are the instrument and control devices contained in the other three types. A word of caution before moving on to the next topic. The physical breakdown that we have demonstrated is both necessary and sufficient. However, there's currently a trend for non-process reasons to fragment units into multiple so-called equipment modules. More equipment entities mean more interfaces, more documents, more testing, more faults, more cost, and more time. Let's examine the reactor to further emphasize this. Since the vessel is the only place that any processing can take place, there are no further candidates to be equipment modules in this unit. It will be possible to mix the batch using the agitator, but that processing is done in the vessel. So that processing is centered on the unit, not on a separate piece of processing equipment. Likewise, it will be possible to heat the batch because of the jacket heating system, but it is again the batch in the vessel that is heated. Even though defining equipment modules based on groupings of control modules is contrary to ISA-88, I have seen collections of control modules like the outlet line here defined as equipment modules in vendor literature. Compare this to the criteria of ISA-88. Do these control modules do any processing? No. Is there any process equipment present? No. Normally, to define a unit or equipment module, there must be some container where processing can take place. There are some exceptions where processing is done in line, like forms of filtration or a batch totalizer. Once again, the vessel is the only place that any processing can take place in this scheme. So, if you have one takeaway from this tutorial, I would advise it is don't forget Occam's razor. Completing the physical design is the point of no return for a batch control project. Moving on. If the physical design is the foundation of batch control requirements, then the equipment entity design is the complete infrastructure defined. Notice also that the equipment entity design is based on the physical design. So in order to explain the equipment entity design, let's first recall the physical breakdown that we derived for our example process cell. This format was useful for explaining the analysis of a process flow diagram, but for the next explanation it will be more convenient to represent the same information in a more hierarchical format. Like this. Here we see the process cell PC1 containing units R1 and D1, plus an equipment module, V1. The control modules in R1 are listed. The instruments and valves for regulatory control are grouped together as they are related. Now, if we add the control requirements for each physical entity in this physical design, we will arrive at the equipment entity design. Now, control requirements in ISA-88 come in three flavors, which are here differentiated with different symbols. Procedural control, which is visualized with a square. Coordination control, which is visualized with a circle. And basic control, which is visualized with a diamond. We will explain what these control types are in more detail, but for now, understand how the equipment entity design is derived from the physical design. We start from the physical design to get our foundation. Then, as we analyze each control requirement, we can categorize it and add it to the appropriate entity. For example, there may be an algorithm needed to say when a process cell can be used to start a campaign based on all equipment being clean and in service. This can be categorized as an element of coordination control and associated with the physical process cell. Another example, we determine that we must be able to mix a batch in the reactor. This can be categorized as an element of procedural control and associated with the physical unit. Each control module must have some control algorithm to make it work. These are all forms of basic control. And so we can continue until all equipment control requirements are categorized and assigned to an entity. Note that each entity can have more than one control requirement. Now, let's explain these three types of control so that you get a fuller understanding. The definition of basic control is control that is dedicated to establishing and maintaining a specific state or behavior of equipment and process. Practically, it is all the control and monitoring that we normally see on a P&ID, including regulatory control loops and equipment-orientated sequences. Here is the reactor again, made more like an actual P&ID by adding the symbols for operator control and monitoring of the various physical control modules. The control implied by the dotted line connections from the HMI or control panel symbol, that's the hexagons, to the physical pump, valve, agitator or transmitter is in fact the most common type of basic control. Although it's normally only implied on a P&ID, we can explicitly add an item of basic control to each of these control modules for emphasis. The diamonds are intended to indicate that. The basic control of the valve will typically allow the valve to be controlled automatically or manually. It will take the request to open or close the valve and put the valve in its requested state. It may indicate a fault if the requested action is not successfully achieved. For a level transmitter, the basic control of this device will take a signal and convert it into a form that can be displayed in engineering units. Regulatory control, normally PID loops, are also a form of basic control. Another common type of basic control is an interlock. For example, it is common to close inlet valves if a vessel high level is detected. Another type of basic control to consider is the sort of control that automates repeatable multiple actions for consistency and convenience. For example, we may want to set a jacket heating and cooling circuit to one of a number of possible configurations. For example, jacket temperature control, vessel temperature control, off or drain. The basic control here would set the regulatory control to cascade when necessary and sequence the hot and cold water supply valves as required. In ISA-88, this sort of repeatable group of commands and basic control of control modules is formally called a compound control module. It may also be useful to incorporate the control scenarios for an agitator in a compound control module. Typical commands might be off, on, time cycle or level control. The nitrogen and vent system here may also be a candidate. For example, a sequence to purge a vessel can be embedded in a compound control module. Compound control modules are useful for semi-automatic control of the plant. They're also useful for reducing the complexity of procedural control, particularly in recovery from faults, but you are not obliged to define any. So I hope you have a feel for what basic control includes. It is closely related to the control and monitoring shown on a P&ID. It includes regulatory control, and it includes repeatable and product-independent sequences. The next type of control on our equipment entity model is procedural control, the type of control that is characteristic of batch manufacturing. There will be more about the different types of procedural control when we get to the procedural control model, but for now, in general, procedural control is control that executes sequences intended to accomplish a specific process-orientated objective or task. Typically, a procedural control element will be adapted with process parameters to achieve different specific targets. That makes it useful whatever process is executing. Here are some examples of procedural control. Add could be adapted by specifying both a material and a quantity to add to the reactor. Weigh. This can be adapted by specifying a quantity. Mix could be adapted by specifying a time to mix for, and so on. Notice what makes this type of control distinct from basic control is that it always affects the batch or batch ingredients. Unlike commands to basic control, which are equipment specific, procedural control commands are more generic. That is because the procedural element has only one specific process-orientated task, like heat or mix, for example, and the commands can only affect how that task is executed. So, all procedural control elements must handle the following commands: start, stop, hold, restart, abort, reset, pause, and resume. Because procedures must respond to all these commands, each procedural control element is actually a collection of sequences that must all be defined. This is a big overhead required in procedural control that is not required for basic control sequences. So, to recap, in general, procedural control is process-orientated, adaptable with process parameters, and handles all procedural control commands. The last type of control on our equipment entity model is coordination control. Coordination control is equally important, but it is a little bit trickier to pin down. According to ISA-88, coordination control directs, initiates, and/or modifies the execution of procedural control and the utilization of resources for batch processing. For example, if an equipment module could be requested by two different procedures at the same time, then an element of coordination control for that equipment module may describe the arbitration rules. It may be first come, first served, or perhaps something more nuanced. In any case, the equipment module can be temporarily allocated to each unit in turn by the allocation control. Here's another example. An element of coordination control may decide when a unit is ready for use by tracking the equipment status, for example, whether it is in or out of service, its state of cleanliness. It may be the philosophy that when a unit is allocated to a procedure, then all control modules in the unit are set to automatic. Maybe only initially, or maybe continually, or maybe the operator is asked to do so. This description would be an element of coordination control too. By categorizing the three types of control in an equipment entity, the ISA-88 framework is guiding designers to ensure that all control requirements are captured in a systematic way. It helps us name every physical and logical resource, and that results in a complete and unambiguous description of the piece of plant that is being modeled. Having defined a process cell infrastructure, we can turn our attention to the design of the procedures for specific products. We start by defining the actual process to make the product by customizing the process model. This model is also described as a hierarchical model. In the case of the process model, the hierarchy is based on processes of smaller and smaller duration from top to bottom. We can think of the hierarchy like a Gantt chart, where the upper levels can be expanded to see more and more detail. We customize this general model to suit a specific process by starting at the top level and breaking the process down following the guidelines. We'll now do this using the example given in the ISA-88 standard. The highest level is called a process, to make polyvinyl chloride in this case. The process specifies the order of processing for an entire batch by defining the order of execution of one or more process stages, which are major parts of the process that usually operate independently. In our example, the first two stages are polymerize vinyl chloride monomer into polyvinyl chloride and recover residual vinyl chloride monomer. Each process stage in turn specifies the order of execution of one or more process operations, which are major processing activities. In our example, the first of these stages, polymerize, is expanded into three process operations, being prepare reactor, charge water and surfactants, and react. Each process operation in turn specifies the order of execution of one or more process actions, which represent minor processing activities. Again, in the example process, the last of these stages, react, is expanded into four actions. Those are add the required amount of catalyst to the reactor, add the required amount of vinyl chloride monomer to the reactor, heat the reactor contents, and hold the reactor contents at 55 to 60 degrees C until the reactor pressure decreases. We've shown the breakdown to lower levels as completely sequential and in equal duration, just to simplify the explanation. However, that is not generally the case. Process stages, operations, and actions may be sequenced in parallel and may be of different durations. We can demonstrate by adjusting the process actions. We have a few activities still to be broken down in the same way, but then we will have a complete process design. In much the same way that the physical design leads to the more complete equipment entity design, so the process design is the basis of the procedural control design. So naturally, its hierarchy is also based on entities of smaller and smaller duration from top to bottom. The highest level is called a procedure. It defines the required set of processing activities for a single batch, typically through the initiation, organization, and control of unit procedures. A unit procedure is a strategy for carrying out all or part of a process stage, typically through the initiation, organization, and control of operations. An operation is an independent processing task to accomplish all or part of a process operation, typically specifying the initiation, organization, and control of phases. A phase is the lowest level procedural control element in the procedural control model that is intended to accomplish all or part of a process action. We can illustrate the close relationship of the procedural control design to the process design by examining the example of procedural control given in ISA-88 to make polyvinyl chloride. The relationship between the process design and the procedural control design is often, but not always, one-to-one. But in the example given in ISA-88 to make polyvinyl chloride, it almost is. The procedure is made up of unit procedures, one for each of the process stages. The first of these stages, polymerize, is made up of an operation for each of the process operations in the process design. The translation of the process actions into phases is the only place in the ISA-88 example where the relationship is not exactly one-to-one. There are only 3 phases defined to achieve the stated 4 process actions. Once again, notice that some elements may execute in parallel. When the model is fully customized, we will have completed the procedural control design. Recipes are the complete instructions to make a product. Once a procedure has been defined, it will form the sequential part of a recipe. For the explanation that follows, we will show just one element for each of the procedural control levels. The template for a specific product on a specific site is called a master recipe. It will consist of a header with placeholders for parameters and any unique identifiers, plus a reference to the procedure to be followed. Normally, each procedural element will be adaptable, with some input process parameters that allow different grades and quantities to be made. For example, temperature set points. Typically, some output process values will be needed to be recorded during batch execution in order to verify the quality of the batch. For example, actual temperatures recorded. When this template is used to initiate an actual batch, the specific values are added to the header, the recipe parameters are plugged into the procedure, and the procedure is started. This recipe is now a control recipe for a specific batch of product. We can envisage a complete procedural hierarchy from top to bottom when it is being executed. Process parameters for a specific grade or batch size of a product are provided to the procedure and the procedure is started. The procedure in turn provides parameters to all the unit procedures that it initiates. The unit procedures in turn provide parameters to all the operations they initiate. Finally, the operations provide parameters to all the phases they initiate. Phases execute, and on completion they return recorded process parameters back up the hierarchy via operations and unit procedures to the procedure level so that they can be associated with the batch product produced. So based on the examples in ISA-88, we see how closely related are the process design and the procedural control design. The first one defines what must happen, whilst the latter describes the steps to make it so. We've also described the place of the procedure in recipes and how recipe procedures execute. We have now discussed the 4 main models that should be customized to fully describe processes in a batch plant process cell. Now we need to understand the overlap between the procedural control design part and the equipment entity design to complete the picture. Dependent on the level of flexibility that's required in a process cell, we can choose how much of the procedural hierarchy to embed in the equipment entity design. Recall that procedural control is one of the 3 types of control in the equipment entity model. In one extreme, we can decide that only the bottom level, phases, will be included in the equipment design. In this case, there will be no procedures, unit procedures, or operations present in the equipment design. Those levels of procedural control will be included as part of a master recipe. This is the most flexible approach and is synonymous with multi-product plants, as many different recipes can be created, constrained only by the functionality of the phases defined in the equipment design. In the opposite extreme, we can decide that all procedural levels will be included in the equipment design. In this case, there will be procedures, unit procedures, operations, and phases present in the equipment design. The only element of procedural control present in the master recipes will be the input and output parameters for the main procedure. This is the least flexible, but can be an effective solution for dedicated plants where changes in grade are all that is required. Flexibility may not even be desirable. The two intermediate approaches are to embed unit procedures, operations and phases in the equipment design, or just operations and phases. Whichever approach is followed, then if we combine a recipe with the equipment entity design, then the complete procedural control is realized. Going back to the most flexible configuration, consider the makeup of each procedural element. Each one can receive some input parameters and a start command. Each can report back some output parameters and a completion status. Finally, each has a sequential part that organizes its subordinates. The way we combine the recipe and the equipment is to have complementary procedural elements in the recipe and in the equipment design. In the case shown, where only phases are embedded in the equipment design, there will be a complementary phase in the recipe for each phase in the equipment design. The recipe phase will map the inputs to and outputs from the equipment phase, but only the equipment phase executes procedural control. In this way, a single recipe phase may map to phases in different units with the same input and output parameters. This is the basis of multi-product plants. In the case where all levels are embedded in the equipment design, there will be a complementary procedure in the recipe for the procedure in the equipment design. However, the recipe procedure will only map the inputs to and outputs from the equipment procedure. The equipment procedure executes all levels of procedural control. A word about terminology here. Procedural control elements that are in the equipment design are prefixed equipment, whereas the levels in the recipe are prefixed recipe. To illustrate this, here we see a complete procedural control design made up of a recipe procedure, a recipe unit procedure, a recipe operation, and an equipment operation, and finally an equipment phase. A word of caution. The term equipment phase means a phase in the equipment entity design. It does not mean it's part of an equipment module. A phase can be in a unit or in an equipment module. Finally, a word about the lowest level of the procedural control model and commands to basic control, ignoring the higher level procedural elements for now. Recall that procedural control only responds to the following commands: start, stop, hold, restart, abort, reset, pause, and resume. The only procedural level that commands basic control entities is an equipment phase. As we have just pointed out, there are though two flavors of equipment phase: an equipment phase in a unit and an equipment phase in an equipment module. It's important to realize that both types of equipment phase are on the same procedural level and both are coordinated directly by operations. That completes this introduction to defining batch control requirements following ISA-88. There's much more detail, especially about recipes and the workflows associated with batch control in the specification. I encourage everyone to read the standard directly. Before signing off, I would just like to offer the following advice on how to follow ISA-88 and keep the batch design optimum and on schedule. For me, the single most important guideline in ISA-88 is to break down the plant into units and equipment modules based solely on processing capability. Processing must be some activity affecting the batch, for example, heat, crystallize, filter, dose, etc. Practically, most processing will be done in units. The original version of ISA-88 identified only two examples of equipment modules: dosing equipment and weighing equipment. It's hard to think of many other processing activities that are done outside of units. Perhaps some forms of filtration, separation, or decanting would be considered minor processing activities and qualify. Some industries may have more candidates than others. In the same vein, ISA-88 is very explicit that equipment modules must execute at least one phase. That is because it must carry out a minor processing action. It is important to be clear that in procedural control, an equipment module phase is not subordinate to a unit phase. A phase is the bottom level of the procedural control model, irrespective of whether it is associated with a unit or an equipment module. Now I want to name the oft-repeated deviations that have become almost mainstream in the batch world. Here be project monsters. The source of the rest of the deviations is probably the unwritten but implicit sense that ISA-88 is a software architecture. This leads to the tail wagging the dog. I have seen in several automation specifications diagrams showing phases commanding equipment modules. This is nonsense. According to ISA-88, the only entities that phases command are basic control. For example, valves, pumps, or compound control modules. It's also common to come across definitions of equipment modules that do not execute a phase. According to ISA-88, this is not possible. An equipment module by definition carries out minor processing actions through the execution of phases. Finally, the definition of equipment modules based on groupings of control modules has become all too common too. This represents a complete departure from ISA-88. Well, thanks so much for watching. I hope it helps in some small way in pointing back to the best practices in defining batch control systems. If you found this to be helpful, or you've got any questions, then I'll be happy to hear from you. This has been James at zavco.com.